Welcome to the first homework of operational amplifiers. In this homework, we're going to review from some of the concepts from previous courses and a few of the material that we covered in the first week. So let's first look at problem number 1. In this problem, we are supposed to do some conversion from linear scale to dBs. Just as a refresher, important thing to remember is some common numbers. For example, if you have a voltage V and it gets amplified to B, it's amplified by 6 dBs, right? How do I know? Well, 20 log of 2 is equal to 6. So now you have that is amplified by not by 2, but 4. Of course, it's 12 dBs and so on, right, with the others. Same thing happens with 1/2. If it gets divided by 1/2, that means it's attenuated by -6 dBs. Or if it's 1/4, of course, it's -12 dBs and so on. So important thing to remember this. The 2 is a very useful number, and the other one is 10, right? Every time a signal gets amplified by a factor of 10, gains 20 dBs. And if it's attenuated by 10, loses 20 dBs, right? -20 dBs. Okay, so that's about this problem. So conversions, hopefully you can do it, or you can guesstimate fairly close without using your calculators. If you look at the number and know the relationship of doubles, quadruples, tens, right, you might be able to pretty much guess the number without actually having to use your calculator. But well, let's go to the next problem. This is an application, so we have a preamp that has an output signal of 47 volts for this particular example, 47, and it produces a gain of plus 15 dBs. So the question, what is the input signal in millivolts? Okay, and of course use 3 significant digits just for canvas. Okay, that's about this problem. Okay, next problem, it's a very basic operational amplifier problem. You have an op-amp, right? And this op-amp has a open loop gain of 200,000. And now we are given the voltage on the terminals. It has in the inverting terminal 10 millivolts. This is the inverting. And on the non-inverting terminal has plus 20 microvolts. Actually, not millivolts, but microvolts. So the question is, what is the output voltage? Okay, very simple problem. Okay, let's go to the next one. The next one is a low-pass function, and we're asked to find the magnitude at a frequency of 80 hertz. So just remember that this is a complex problem, has a magnitude and phase. In this particular problem, we're asked to find the magnitude, but remember that S is not a real number, right? It's a complex number, j omega, and omega is in radians per second. We have to remember to do the conversion. Okay, the next one is find the phase at 85 degrees, similar problem, but instead of the magnitude, we find the phase and in degrees. Okay, the next one probably is a body plot problem. So we have a circuit that has a single pole and has 1 0 at 0, right? The question is to find the transconductance as a DC parameter and the value of the capacitor such that this transfer function is implemented with circuit given. So you have to find the transfer function in this domain, right? Change the capacitor by 1/SC, find the transfer function, and this one here is the location of the pole. So when you find the transfer function, you are going to find a first order function, and the location of the pole has to match this particular frequency given by this diagram. And the other thing is that at high frequencies, when S goes to infinity, right, the gain is 26 dBs. So in the numerator, you are going to have some constant, and that constant has to be equal to 26 dBs. Okay, next problem. It's a very basic operational amplifier. This is just to remind basic analysis. So we're given the values of the resistors, and the input voltage. You just have to identify what configuration is this operational connected into, and apply the very basic operational amplifier techniques. That in this case, the most simple one, right, is that in an ideal amplifier, the difference between the positive and the negative terminal is fairly close to zero, right? Because the gain is supposed to be infinity, and the current entering the amplifier is zero, right? So there is no current coming in. That's the two conditions for ideal operational amplifiers. Okay, same thing with this circuit. In this, we have a current. The current cannot come in or out of the amplifier, so it has to go to resistor 2. And the voltage across the inputs is close to zero for an ideal op amp. Just find the output voltage. And that's pretty much it. A very simple problem. Hopefully you do it right. Okay, thank you.